Hi, this is my video for Lab 4 Macroscopic View of DC and RC Circuits. Introduction. The purpose or goal of this lab was to predict the behavior of circuits that have resistors in series and in parallel, as well as to use multimeters to measure the actual values of conventional current and potential differences, and to understand the behavior of ohmic resistors and capacitors. The fundamental physics principles used in this lab were the loop rule for energy conservation and the node rule for charge conservation, as well as the principle of steady-state conditions. Series circuits was the first part of this lab. My initial setup for the model is shown to the right, using 2 ammeters, 2 batteries, and 2 resistors. The ammeter readings after connecting the batteries read as 0.02 amps on both ammeters. After the connection was reversed, the first ammeter, it read negative 0.02 amps. After replacing one ammeter, the first ammeter, with a voltmeter, the voltmeter read 3 volts and the ammeter read 0 amps. After removing the voltmeter, closing the circuit with a wire to measure potential difference, the ammeter once again read 0.02 amps. For this part of the lab, we were to measure the potential difference at multiple points around the circuit. So for my arrows, I used it going from the red wire, which is positive, to the black negative wire's location. So as shown in the figure to the right are the locations for each letter. Location from B to A, I found the potential difference was 3 volts. Whereas from A to H, H to G, and G to F, all were 0 volts. From F to E was negative 2.0 for 1 volts, E to D 0 volts, D to C was negative 0.959 volts, and C to B was 0 volts as well. So adding all these individual potential differences up for a round trip around the circuit adds up to 0 volts. Below is the graph of the potential relative to the negative end of the battery versus the positions shown around the circuit. When you attach the voltmeter, even though the circuit is changed, the ammeter reading does not change because the current flowing through the circuit from the batteries does not change as well. Ammeter reading after connecting a voltmeter across the 100 ohm resistor was 0 amps. When the voltmeter is replaced by an ammeter in parallel with the 100 ohm resistor, the current to the other ammeter, ammeter 2, increases to 0.06 amps. The calculations for the series circuit model were to calculate the resistance for the 47 ohm resistor, the 100 ohm resistor, the wire, and the ammeter. I used the formula delta V over I, representing potential difference divided by current. For the 47 ohm resistor, I found that the actual resistance was approximately 47.95 ohms. For the 100 ohm resistor, calculated to be 102.25 ohms, and for the wire and the ammeter, the resistance was calculated to be 0 ohms. The second part of this lab was RC circuits. The components used in this example were a 10 ohm bulb, a 20 ohm bulb, a 9 volt battery, and a 0.2 farad capacitor. The goal of this was to observe how a capacitor charges, and shown below is the original setup of my model. After the 10 ohm bulb and capacitor are connected to the battery in series, the light bulb shines for a few seconds before dimming out, thus the capacitor is charging. And after disconnecting the battery and attaching the 10 ohm bulb directly to the capacitor discharges. Using a 10 ohm bulb, to charge took 19 seconds approximately, and to discharge took 18 seconds approximately, give or take a few fraction of a seconds. Using the 20 ohm bulb, a charge for 40 seconds to charge and approximately 38 seconds to discharge. In the second example of RC circuits, the components used were a 9 volt battery, 0.2 farad capacitor, and a 30 ohm light bulb. The voltage across the capacitor was 0.042 volts. I took data every 5 seconds up to 20 seconds for the discharging data and found a slope when I plotted a straight slope or linear slope of negative 1.1371 when I plotted the ln of delta V over delta V naught versus time. From these calculations, I found that the RC value, which is equal to the slope is equal to negative 1 divided by the RC value. From the slope of negative 1.137, I found the RC was approximately 0.88 seconds. Questions, conclusions. What if you were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter? The current measured would be lower because real ammeters have some amount of resistance. What if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? The model used in this lab would predict the capacitor to be fully charged instantaneously if there was no resistor included in the circuit. However, in real life, the capacitor would still take some time to charge due to the inherent resistance of the capacitor. That's it.